All right. Here we go. In the Desmos activity yesterday, you went through playing with like the sliders to mess with the values of like the A's and the B's in some sine and cosine equations, polar equations, where it was R equals, so that you could see how the A affected the shape or how the B affected the shape. So one of the first ones you looked at was circles in polar form. And so the equation is in this format, R equals A, and then it's sine or cosine of theta. Okay, so when you see the equation in that format, you know that it's going to be a circle. We talked about in our previous notes that if you just had R equals a number and there was no theta, that was a circle also, right? But if it was R equals a number and there was no theta in your equation, it was a circle centered at the pole, and that R was the radius. The difference here is these circles are not centered at the pole. So we've got cosine versus sine. The difference is going to be which axis the circle is drawn along, okay? Because it's drawn in a direction, okay? The edge of these circles is at the pole, okay? But they go out along the axis. So you can see if it's a cosine equation, it is drawn along the horizontal axis, what you consider the x-axis in a rectangular coordinate system, right? And then if it is a sine equation, it is drawn along the vertical axis. Bless you. What you're used to calling the y-axis in your rectangular coordinate system. And that should make sense to you because if you think about your unit circle, all those ordered pairs around the unit circle, x is cosine and y is sine, right? So if it's a cosine graph, it's drawn along the x-axis. If it's a sine graph, it's drawn along the y-axis. Okay, now what would make it different would be if that A value was negative instead of positive. So in these two examples, you've got a positive A drawn, and the A is the diameter of the circle. So if it was a negative A for cosine, your graph would be over here on the left side, still along the x-axis or the horizontal. And if you had a negative A in front of the sine, it would show up on the negative side of the vertical axis. Does that make sense? And some of you may have already inferred that from the Desmos activity yesterday. You may have kind of already taken some of those notes or written some of those things down. So far, so good with circles? Oops. Hang on. Away over here. Okay. So if I want to sketch these circles, let me out a little. There we go. So if I want to sketch these circles, I first need to identify if it is a sine or cosine function, because that's going to determine the direction that my circle is going from the pole, which edge of the pole is going to, or which edge of the circle is going to be on the pole. Okay, so for this first one, A, this is a cosine equation where A is 2 and it's positive. So positive cosine means it's going to be on the right side. So the left edge of the circle is going to be at the pole. This is going to be the left edge. And the diameter will be 2. So I'll go over 2 to the right, and that'll be the right edge of my circle. So then I can just sketch my circle over here. Now, it's not going to be perfect. If you would like it to be perfect, if you are a perfectionist like that, I do have a drawer full of compasses over there, and you're welcome to get a compass to help you draw perfect circles, but I'm not worried about it. A sketch is fine, okay? All right, this one is negative sine, so it's going to be drawn down because its sine is vertical, and the negative means it's down. So this is going to be drawn below the pole. So the top edge of the circle will be at the pole. And then the diameter is 3. So I go down 3. And this would be the bottom edge of my circle. Try to get a thicker line to draw these. You can see my diameter is the A. It's 2. It's drawn to the right of the pole. My diameter is 3, and it's drawn below the pole because this is negative sine. Everybody good so far? That was drawn to below. This was drawn to the right. What direction is this going to be drawn? To the left of the pole. And it's got a radius of 5. So the right edge of the pole, the right edge of the circle is at the pole, and the left edge of the circle is over here at 5. That diameter is the 5. Think circles are pretty straightforward. Do y'all feel okay about circles? If you want to, at the top of this, where we had a little space, you could put just a little reminder or a refresher that just R equals a number is also a circle. But that one is centered at the pole, and the R is the radius. Okay, so that's also a circle. Okay, it's centered, it's drawn differently. It's this, the pole is the center of this circle, and it's got a radius of whatever this number is. Okay, so those are the different types of circles in polar equations. All right, so here's where it starts to get a little more complicated, is with limacons. In the in the Desmos activity yesterday, you had some equations that were graphed where you got to play with a little slider to see the A and the B change and how that changed your limacon, and what direction they went on based if it was sine or cosine, which is similar to the circles. If it's cosine, it's going to be drawn along the X or the horizontal. And if it's sine, it's going to be drawn along the vertical. But the Desmos activity didn't go into detail about what those different types of limacons are. So there's actually 4 different types of limacons, and it's all based on this ratio of A to B, okay? So again, if it is cosine, the positive or a negative goes with the sine or the cosine. That's just that positive or negative there is telling us the direction that we draw the limacon. If it's going to be left or right if it's cosine, or up or down if it's sine. Okay, the A and the B, those are positive numbers. They're greater than 0. We're just looking at the values. Don't worry about this sign. Does that make sense? Okay, so when we compare the ratio of A to B, okay, there's 2 ways you can write this. I'm going to write it both ways, and you can refer to whichever one makes more sense to you. But if the A to B ratio is less than 1, What does that mean? How are A and B related to each other if this ratio is less than 1? Which one would have to be the bigger number? B, right? So if A is smaller than B, if A is less than B is another way you could write this. This is going to be called a limacon with an inner loop. When you were playing with this sliders on the thing in Desmos, you may have noticed sometimes that you got this shape that looped around inside itself. Did y'all notice that on any of them? Okay, that's a limacon with an inner loop, and that only happens when the A is less than the B. If the A to B ratio equals 1, what does that mean? How are A and B compared to each other? They're the same. So if A and B are the same value, this is going to be a different type of limacon, which is called a cardioid. Okay, you can probably use some root word knowledge there. What does that sound like? Cardioid. Cardio, cardiac, right? What does that mean? That's heart. This is kind of a heart shape. It's the one that comes to a point instead of looping in on itself, it just like meets at the pole to make like the top part of the heart shape. Okay. The next one is if your A to B ratio is greater than 1, but less than 2. Okay. So B is going to be bigger than A, or excuse me, A is going to be bigger than B, but not twice as big. Does that make sense? So I'm going to write it that way. I'm going to say A is going to be between B and 2B. So it's bigger than B, but not twice as big. If that's the case, then this is going to make what's called a dimpled limacon. Don't know what a dimple is? And that's exactly what it looks like. It's got like it dimples in. It does not loop in on itself. It's not a full loop. It's just got a little dimple on it where it kind of concaves in a little. Okay. No, the cardioid comes all the way back into the pole at like a point. And I'm going to draw a picture of these for you in a second so you can see the difference. The dimpled limacon is going to dimple in, but not come all the way back to the pole. Okay, good question. All right, and then last but not least, what if the A to B ratio is greater than or equal to 2? What if A is twice as big or bigger than B? So A is double B or bigger. If that's the case, this is a convex limacon. Okay, all of these first three were concave. They come back in. Convex means it doesn't cave in, right? Okay, it bows out. This one's going to look kind of close to a circle, but it's not going to be a perfect circle. It's not a radius, an equal radius all the way around like a circle. It's going to kind of look like a rock. Like one side's going to be more rounded and it's not, the other side's not going to be completely flat. It's going to convex out a little, okay, but not as much as the other side of it. Okay, so I'm going to draw an XY axis in all these boxes so that we can draw an example of sine and cosine of these different shapes. So go ahead and just draw an axis in each of these. Vertical and horizontal axis. We're just going to draw them all positive for the sake of our notes. The only thing that will change if there is a minus between the A and the B, it'll change the direction along the axis that it's drawn, right? If it was cosine, it'd be drawn to the left if it was minus. If it's sine, it'd be drawn down if it was minus. We're just going to draw them all positive for now, though.
This is like dumb. What language is this on from? That's the little thing under the C.
Yes, I believe it's Latin.
Good.
No, we can look it up though. When we finish these notes, I'll look it up and let you know. I've looked it up in the past and I think it came from Latin, but I don't remember because it's been a few years since I looked that up. All right. So again, sine is going to be drawn along which axis? Sine is going to be drawn along the vertical. Cosine is going to be drawn along the horizontal. Okay, so we said limacon with an inner loop. If it's sine, we're going vertical. So it's going to have like this small loop inside of this bigger limacon. Now, all of these limacons are symmetrical. Okay, they all have line symmetry if you were to cut them in half. I'm freehand drawing them, so they may not look perfect, but they should be symmetrical. Okay, so notice this does have pieces that come below the horizontal axis some. Okay, and then this inner loop comes in. Okay, so that's the general shape of a limacon with an inner loop. If it's sine. If it's cosine, it would be the same shape, but drawn along the x-axis this way. I didn't draw that nice and symmetrical. I should have been up a little higher over here, but you get the idea. Right? Now, the relationship between how far out this end comes, this like the top of the limacon, the height of it from the pole, or how far in that loop comes, or how wide these come out, that's all based on the A and B value as well. We're going to talk about that in a little bit. Now the cardioid, this is the one that we said was heart-shaped. Instead of looping in on itself, it just comes here to the pole and then comes back out. So it looks more like this. Now it's still rounded on this end. It doesn't come to a point like you usually draw a heart on the bottom of the heart, but the top part of the heart shape looks like that. So then if it was a cosine, it would be the same thing. It would just be drawn along this axis. A limacon, a dimpled limacon looks, it's kind of like a bean shape. It's going to come below down here, but instead of how the cardioid comes all the way back into the pole, kind of like as a point, when it comes back in over here, it's not going to come all the way to the pole. It's going to stay below the pole, okay? And it's not going to be a sharp point. It's going to be a little more curved. So it's going to end up looking something like that. It's got this little dimple in there. And if we draw that along the X, or excuse me, the horizontal axis, depending on how tall and how wide it is, like the way I drew this one looks more bean shaped. This one looks almost like more guitar pick shaped, but you know, that's kind of the general shape of it. Okay. And it can be taller, or that's all going to be dependent on the A and the B, what those numbers are. All right, and then last but not least, the convex. Instead of coming in at all, whether it's just a dimple or all the way to the pole or completely looping in on itself, it bows out here instead of coming in at all. It's convex instead of concave. Okay, so it almost looks flat. It is not perfectly flat on that side, but it almost looks flat. It's kind of just like a rock. I don't know. Oh, the way I drew that one kind of looks like a perfect circle. It is not a perfect circle. Okay, if you want to make a little asterisk and put a side note, not a circle, you can. So far, so good. I'm going to look up Amazon. See where it comes from. I don't need to know about the math of it. I want to know where the word comes from. It might be French. Oh, yeah. Limacon of Pascal was discovered by Etienne Pascal, who's French. Okay. Yeah, because it's kind of snail shaped, I guess. Interesting. All right. Now, when we go to graph a limacon, if we're graphing by hand, these little 5 steps here are going to help you plot 4 points to your limacon. Okay, so looking at these, it's going to be the like top, or if it's a cosine, it's not going to be the top. It's going to be like the furthest out, left or right, right? Okay, so we're going to plot that point. Okay, and then we're going to plot the points along the other axis. Okay, we're going to call that like the stretch of the graph here. And then we're going to plot where it comes back into, whether if it's an inner loop, that would be the inside of the loop. Or if it was a cardioid, it's just going to be at the pole. Okay, if it was dimpled, it'd be this point here on the axis. Or if it was convex, it'd be this point here on the axis. So these steps are going to help us come up with, like, it's just 4 points to plot, and we'll know the general shape and we can kind of sketch it. It's not going to be super accurate because you can see we got all this. It's only the points on the axes that this is going to tell us. We want to get points within the quadrants to figure out exactly how rounded this is up here. You can always make a table of values because we know polar coordinates is if I plug in the angle, I can calculate what R should be, how far out from the pole it should be there, right? So you can make a table of values to get additional points. Okay, but these 4 key points here is what these steps are going to help us come up with. Okay, so the first step is to determine if it's sine or cosine, and so we know what direction that we're drawing this out. Is it going to be a vertical or horizontal limacon? And even once you know whether it's horizontal or vertical, which direction? Okay. Okay, then we're going to find our ratio A to B so that we know which type of limacon it should be, what the shape is. Should it be a cardioid? Should it be dimpled? Should it be convex? Or should it have an inner loop? And then when we get the sum of A and B, this is going to be that top point, like the height from the pole. How high up, or if it's cosine, left or right, is that furthest point from the pole. Okay, I'm going to call it the height. And I'm going to put that this is along, I'm going to call it the main axis. Okay, the main axis is determined by whether this is sine or cosine, right? If it's sine, the main axis is the vertical. If it's cosine, the main axis is the horizontal. Now, A in and of itself is what I'm going to call the stretch. That's how far along the opposite axis we go to get the width of the graph there at the axis. So the stretch or the width along the opposite axis. And this is in both directions. That's how far you go from the pole in both directions along the opposite axis. And then the difference when you do A minus B, that's going to be what we're going to call the lower point. It's like on the opposite end of the height. The thing is, though, that lower point could go in the same direction of the height if it's an inner loop, right? If it's an inner loop, A is less than B, correct? So when you do A minus B, if B is bigger, you're going to get a negative number here, aren't you? So I'm going to make a note. If you get a negative when you do A minus B, that means that you're going to go in the same direction as the height to plot this point, because it's an inner loop. But if you get a positive number when you subtract, you're going in the opposite direction as your height. Now, what if you get a 0? What does that mean? That means it's a cardioid and you're just going to be at the pole, right? You don't go anywhere. I'm going to color code this for us. We're going to do the height. Stretch. And the lower point. So far, so good? All right, let's try it. Let's do some of these examples. First of all, I'm going to identify whether it's sine or cosine, positive or negative, so I know what direction I'm going to go in. Okay, so I'm going to go ahead and write that out. What direction is this limacon going to be drawn for A? To the left. What about for B? To the left also. It's negative cosine again. Okay, and what about for C? Hold on, my pen just stopped working. I don't know what's going on. That's going to be the left. Okay, and then we said C will be down because it's negative and it's sine. Okay, so that's the direction the limacon's going to be drawn. Okay, now then we want to know the shape. So I'm going to identify, first of all, what is A and what is B. So what's in we'll do problem A first. Okay, A is 1, B is 2. So if I do my ratio, no, the negative is telling us the direction. We're not worried about the sign. We just want the numbers. No, that's what I was saying. Here, we want to just look at A and B greater than 0. The positive or negative goes with the sine or cosine, because that's just telling us direction that we draw the limacon. Okay, so as far as the ratio and all of this goes, we don't need to worry about the minus. Okay, so this is less than 1, isn't it? So what shape is this? Going to have an inner loop. Okay, A plus B. So we want to do the sum. So 3, that's going to be how far I go out to get the height. That's going to be the point furthest, in this case, to the left, we said, from the pole. And then A in and of itself, we said is 1. That's going to be the stretch along the opposite axis. In this case, that'll be up and down. And then A minus B, we get a negative. That's because there's an inner loop that comes out negative. So that is going to be where our lower point is. It's going to be 1 unit in from the pole in the same direction as the height. That's what all that information tells us. So the to the left, my height is at 3. 1, 2, 3. My stretch along the opposite axis is 1. So up 1 and down 1. And the lower point's at -1. So that means I go in the same direction I went for the height. So that's to the left 1. So those are the 5 points I can use, or excuse me, 4 points I can use to draw my limacon with an inner loop. So it's going to loop into here, and that's going to go through there. Ooh, hang on. That was not pretty. Try that again. Still not pretty, but a better representation. Let's see what colors I used. I used yellow, orange, green. Okay. This point. These 2 points. And this point. That's how I got those. And I knew it was an inner loop, so I knew the general shape. Now, that is not a very accurate one because, well, one, my pen is kind of lagging, so technology, but also, like, I went higher over here than I did over here. That's not perfectly symmetrical. It should be. But that's the general shape of it. Now, if I wanted to get this more accurate, I've got these lines drawn. This is at, what, 30 and 60 degrees, right? In each quadrant, it's the 30 and 60 degree reference angle, these lines that are drawn out. I could make a table of values. I could come up here and I could plug in 30 degrees and solve this and see what R is and say, okay, at 30 degrees, this is how far out I should be. At 60 degrees, at 120, at 150. I could go and plot additional points by making a table of values. Do y'all understand that? So that's how you could make it more accurate and to see exactly how far out these pieces should go and how far out these pieces should go. Does that make sense? Okay, so let's try. I don't know if we have time for, how much time do we have? I'm going to skip to C since we just did a cosine one. If we have time, I'll come back and do it, but let me do a sine one with y'all real fast. All right, so it's sine, it's going down. A is 3. B is 2. So the A to B ratio, A is bigger than B, but not twice as big. So what shape is this? This one is going to be dimpled. Okay, and then A plus B is 5. So that's going to be the height. A is the 3. That's going to be the stretch. And A minus B is +1. That's going to be the lower point, and because it's positive, that means it's going in the opposite direction as the height, right? So my height is going, we said down. So my height 5, I'm going to go down 5. The stretch is going to be along the opposite axis. So this is left and right in this case. I'm going to go 3. And then the lower point is positive, so it's in the opposite direction of the height, so it's up 1. Now, this is dimpled, so I'm not going to bow this out here through that point. I know that it has to come out higher than that over here and dimple back into it. You got to make sure that it is that dimpled shape. Does that make sense? Now, how far out these come past the dimple? I could make a table of values to get those more accurate, but this is just the general shape of it, the general location of it. Does that make sense to everybody? So y'all have one that I want you to try. It says try on your own, and go ahead and do this one that we skipped also, and we can check those tomorrow. So try those two. If you need to go back and play around looking at that Desmos, you can go back to it and play around with the sliders and kind of see how it changes from inner loop to cardioid to dimpled to convex, and you can play around and get nice visuals of those. Is this making sense so far? Okay, good. Stop this recording.